Hello, my name is Nicole Norwine, and my project presentation is on polymer membranes for reverse osmosis desalination. So a little bit of a background. Desalination is the process of taking or filtering out minerals or salts from a substance. Reverse osmosis uses a force, pressure, and concentration gradients to separate salt from water by forcing it through a semi-permeable membrane. Polymer membranes are the most common membrane used in desalination technology due to their superior qualities. And then polymer membranes make desalinate water more affordable, and the grades are based off of aromatic properties. In the industry, thin film composite configuration is the most common configuration used, and they are produced through interfacial polymerization. Some material properties. In general, polymer membrane properties include self-limiting kinetics, self-healing nature, tunable barrier properties, superior flux and sensitivity. And for nylon membrane properties, as used in this experiment, they have dysfunctional hydrophobic and hydrophilic monomers that work together. They have higher mechanical support, high hexane partitioning, fast diffusion rates, and high film permeability. In a journal article used for the background of this research, they looked at fluid shear, diffusion rates, capillary responses to stress, capillary responses to heat, bubble formation, elastic crumbling for deformation of membranes. And then in a closer look at the membranes for polymer membranes, here are the molecular structures, as you can see under microscopes at varying scales. And here's another look at the molecular structure based off of some molecular properties. And then as for this experiment, let's start with materials. I used a membrane phase and pump system that simulates a very small bench scale, one phase pass through desalination phase. And then as for the membrane itself, I used acetate, nylon, and screening material, and then a PVC core. I used a refractometer to measure the saline levels in our salt water. Salt, gloves, super glue, plumber's wrench, towel, scissors, and water were the other materials in this experiment. And a little bit of an experimental overview. There are two experiments conducted. One was experiment one, the one pass. And this was what would happen if we only ran the salt water through the membrane once. So what would be the time of one pass? So the first indication that water has gone completely through the membrane. And then how long did it take for a 4-gallon volume container of water to go through the membrane? And then what was the change in saline from start to end? And was there any fouling or any other physical changes such as turbidity of the water that could be assessed? And then in experiment 2, there was a 2-hour continuous run where the water is recirculated through the tank and through the membrane phase, and the change in salinity and any physical changes was recorded then as well. So let's look at deeper into the membrane I used to simulate a polymer membrane based off of what would be industrial standard and in the background research. So the first layer would be the support. So I used pool screening because that was what was available to me, and that simulated the netting and or support layer of the membrane. And then the active layer would be the acetate sheet. And then the final layer would be the polymer or polyamide membrane material, which would be nylon. And that was a pore size of 0.22 micrometers. And then this would continue on for another 5 layers. And commercial grade or normal lab scale grade membranes, there would be much more layers, much more fabrication. I just did not have the means to do so. And then for experimental procedures, I cleaned and sterilized my workspace and my equipment. I fabricated the membrane. I mixed salt water together, so it was just salt and deionized water, which had no added contaminants or anything like that. I inserted the membrane into the membrane phase and secured it tightly to ensure that there'd be no leaks. And I started the timer and conducted the experiment, and then recorded the results based off of the experiment I was conducting. So change in salinity, physical properties, any degradation of the membrane, fouling, etc. And then here is a video of my experiment that I implore you to look into closer. It is a bit slow, so I'm just going to push it along. You can see the membrane materials closer. And that's the finished one while it's fabricated with glue, which is not industrial standard. Here is a look at the membrane that you saw at the beginning of the presentation. That is the membrane used in both experiments. Being inserted into the membrane phase, the refractometer, as you can see, I worked at hypersaline levels to really push the salt concentration. Here's the membrane phase and tank, which was a 5-gallon bucket. I used 4 gallons of it. There's the pump system and piping, and then the membrane at the end of the experiment. So for results, in experiment 1, so yet again the 1-pass experiment, we start with a salinity of 34 parts per thousand, so just on the border of saltwater and hypersaline levels, and that saw a change in salinity of 4 parts per thousand, which is very high, and that was with 1 pass at 18.72 seconds. That was when the first obvious sign of all of the water going through the membrane at once, and the first output was at 18.72 seconds. And then the total time to have all 4 gallons of water go through the membrane was 1 minute, 43 seconds, 79 milliseconds. And minimal fouling was observed, so there wasn't much degradation on the membrane at this point. As for the 2-hour run, I used time intervals of 10 minutes, 30 minutes, 60 minutes, 90 minutes, and 120 minutes. And the change in salinity and any physical changes was also observed. Yet again, there's very minimal fouling, and then the turbidity of the water actually improved over this experiment. And then as you can see in the chart, you can see the difference in the salinity levels. As you can see, there is a large change between 10 and 60 minutes, and then it stayed pretty steady. So in conclusion, desalination will be an important resource needed for the future water needs and demands. Polymer membranes will continue to make desalination more affordable as they're optimized. Polymer membrane structure has superior qualities in comparison to other membrane materials. Minimal fouling was observed on the membrane, showing superior mechanical properties, flux, salt rejection, recovery in this experiment. And then the experiment shows approximately 2 parts per thousand salt rejection at a very small bench scale over that 2-hour period. And then the membrane can be improved by interfacial polymerization and possibly heating of the water. Any questions?